Welcome back to Fat Mama Physics. In this video today, we're going to look more closely at speed versus velocity. This video will be mostly focusing on instantaneous, the definition between instantaneous versus average, what do those mean, as well as going over an example. By this time, you should have a little bit of idea what speed and velocity means, but I will do a quick recap with us. So, I have up here speed, velocity. Key thing is that your velocity is a vector, meaning that it will have a direction. So whenever you are reporting, whether you are giving a final answer and it is a velocity, you must include directions. If you don't, it will cost you. Okay, so please be careful of that one. The other in terms of calculations, you'll find that when you're calculating for average speed, you don't need to worry about in which direction your object is moving in. All you need to do is count up the total distance and divide that by the total time. And you can kind of think of it as, okay, how much calories am I burning? It doesn't matter where you're going, as every step counts. For average velocity, not quite the case. You are looking at the total displacement. How much has your position changed from the beginning versus the end, and divide that by the total time. That's almost as if you close your eyes and you only cared about what happened before and after, okay? Please note that these two equations are not in your data booklet. You are expected to know them by heart. And a shorthand for writing this is your velocity and or your speed, whichever one you're using. And because the equation looks so similar, V equals to S for displacement or distance for that matter, divided by the time. Now, if you are a triangle person or you could use VT and then S, similar to how you would multiply and divide for your problems. Okay, so let's get on with the thing I want to go over today in this video: instantaneous versus average and what those mean. So I'm actually going to demonstrate this using one of my favorite PhET simulations, the moving man, right here. Okay, so what this one is showing you is I have a man, there's a ruler here. Notice that there is a reference point in the middle of 0 meters. And whether he is right of that line or left of that line tells you the displacement. Positive on the right, negative on the left. Okay, so that's his position. He's at 0 meters right now. It tells you velocity in meters per second, and his acceleration is not something we're going to go very much in detail today, but we will talk about acceleration next, of course, or in the future. So for the moving man, and if I move this guy, I can just click on him and I just move him around like this. Okay, now you might notice that as I'm moving him, all of the toggles are going crazy. But if you take a look at the position is showing where he is relative to the zero line. Notice the time is ticking, and notice in between and we can ignore acceleration for now. Take a look at his velocity. Notice that his velocity is constantly changing as I am moving him, because my mouse clicking skills and my moving my mouse aren't, it's not very perfect, but it's going everywhere. Now, if I caught a particular moment, for example, at 42 point whatever, we can track his velocity at that specific time. And that velocity at that specific time is his instantaneous velocity. Right now it's 0 because he's not moving. But notice it's constantly changing, and if I just picked a particular time, if I took a screenshot of this, actually, let me do that right now. Okay, so I'm gonna keep moving him. In fact, it doesn't matter. If I just kept moving him, and I click print screen at one point, okay? And let's paste it onto this Paint app that I just opened. Now, if I had to take his instantaneous velocity, it's like taking a snapshot. At 112.12 seconds, his velocity was 15 meters per second to the right. That is called the instantaneous velocity. Velocity at 1 point in time, okay, at a specific instant. So that's the key thing here. It's the velocity at that specific instant. Now, what if I ask for speed? I mean, speed, I could just tell you 15 meters per second. I don't even have to tell you it's going towards the right. So that's what instantaneous means. What if the man was moving at a constant velocity forward at 2 meters per second? So what is his instantaneous velocity after 5 seconds? So the key word here is the constant. Constant means that this man is moving at the same velocity and that it's not changing, okay? So even after 5 seconds, if his velocity doesn't change, he's still moving at 2 meters per second. His instantaneous velocity is not changing throughout that time. But what if this man's velocity was changing? Let's say he was accelerating. So let's go back here and to the FET simulation, and let's model that. I'm going to put him all the way on the other side. Oh shoot, he just crashed. Oh, maybe there's some sound feedback. Okay, so let's clear the time. Oops, pause and clear the time. And then I will set his acceleration. I'll give him some positive acceleration, going in the forward direction, meaning he's going to keep going forward and he's going to speed up going in the forward direction. So this is just showing that his velocity is changing. It's okay you don't quite understand acceleration today. We'll go over more of that in detail. The key here, what I want to do is I want his speed to change, okay? So let's do that. What if his speed was changing? And I'm going to press the play button and I'm going to pause it when he hits the other side of the wall with a bang. Look at that. Look at him go. Look at his velocity change. Da, 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 da. Okay, so there we have him all the way at the very end. Notice his velocity was constantly changing as he moved. Okay, so it says, so you can see his velocity going up in terms of a numerical value. That's just the same thing as you're driving and you're looking at your speedometer and the needle moving up and around, showing you that your speed is increasing, okay? So notice the difference here. His instantaneous velocity was changing the whole time he went across the map, okay? So his instantaneous velocity changing. So that's an example of his instantaneous velocity changing, okay? Now, what does that mean in comparison to what we call the average velocity? What if we wanted to find the average velocity? What does that mean? As opposed to finding the velocity at a specific moment or a split second in time, the average is looking at the weighted average. And the weighted average, we're looking at the weighted average for a specific motion. It's the whole duration of that specific motion. So we're looking at, for example, let's take this moving man. And let's say the specific motion we're interested in is when he started from negative 10 meters and he crashed all the way at 10 meters on the other end. If we look, we could find his average velocity for that entire trip. His instantaneous velocity was constantly changing, but for his average, let's take a look at what that means. Okay, so if you looked at the top, we could use these equations for average speed and average velocity. Let's do an example. Let's do a quick example here. Now, you might be thinking, well, how do we find the average? His velocity was constantly changing. Could we take the average of all of those? Do we have to take a snapshot every 0.1 of a second and calculate the average of all of that velocity? Calculate the average of all of those? No, you don't. There's a quicker way and a more straightforward way to do that, and that's looking at the total displacement. What was his total displacement versus his total time? So what could we do for that? Okay, so the moving man. So his total displacement was a total of 20 meters because he started negative 10, he went 10 to 0, and another 10 meters all the way to positive 10. Total of 20 meters in the positive direction. The time he took we can use the time that the simulation uses here, 6.4 seconds, 6.4 seconds, and we punch that into our calculator. 20 divided by 6.4, and we get 3.125. 3.125. We round that to 266 because that's what the PhET simulation shows us for the time. That gives us 3.1 meters per second to the right. And notice I included the directions. So this is how you would calculate the average velocity. And notice that the average velocity is describing the whole motion. It's not necessarily saying a particular velocity for a specific time. We don't know that. Okay, we would have to actually track the motion second or point a millisecond, if not a microsecond, to find the instantaneous velocity, which is why it's actually difficult to calculate by hand. So your instantaneous velocity is not as opposed to average is difficult to calculate by hand. It's much easier if we use a position time graph, not something we will cover in this video today. Okay, so that's how you would find the average velocity. You look at the whole time, whole duration of the motion. Okay, with that, let's try an example. So I will do example 1, and I will give you a chance to try example 2. Anyone play Final Fantasy? Haha. Okay, never mind if you don't. But anyways, a chocobo, and if you don't know what a chocobo is, it's okay. It's a very random object I picked. It's a bird, essentially. Some sort of a bird, big beak, some feathers, okay. Alright, so we have a bird, and the bird is going to run at 22 meters per second for 45 seconds. That's his first motion, and then 33 meters per second for 75 seconds. What was the chocobo's average speed? Okay, so every time when you first started with the question, good idea, number 1, to draw a picture. It helps you visualize what's happening. Notice the chocobo runs at a smaller velocity and then a larger, actually I should use speed because, anyway, so we could 22 meters to begin with, then at a faster speed and for a longer time. So I'm actually going to represent that pictorially with a picture and a longer arrow for his second motion. Okay, so notice he traveled a longer distance in the second segment than the first one. Okay, you're wondering how did he speed up in such a short time? Okay, it's not quite possible, but for the sake of simplicity, let's say the chocobo right after 45 seconds jump sped to 33 meters per second without any sort of speeding up. It was just instantaneous change. Now we know that the equation for the average speed is total distance divided by total time. So let's find the chocobo's total distance that he traveled and then his total time. If we divide the two, we could find his average speed. Some of you might think, well, what about if we took the average between 22 meters and 33 meters? Couldn't that give us the average speed? Now that's where we have to be very careful, because notice that he didn't travel for equal time for these two velocities. So in terms of the weight, when we go back and we look at the weighted average, it means that you need to weigh 22 meters per second, equivalent to how much 45 seconds would take during the whole duration of this chocobo's motion. Okay, so if we try to take the average, it doesn't work that way because the weights are different. The time weighting is different. It's like how your quizzes are weighted much less than your tests, okay? So you can't just take the average of the two numbers. It's much easier just to do in terms of the total versus the total distance over the total time, okay? So that's something to be careful of. But how do we find a total? How do we do that? Well, we do know that the total time is the two times added together, 45 seconds and 75 seconds. That gives us 120 seconds total, okay? But what about our total distance? Total distance, okay? How do we find that? Well, let me do a little bit of labeling. I will label the first segment here. Let's say this first distance that the chocobo traveled at 22 meters per second is A, SA, and S is for displacement. It's in your data booklet. I know it sounds more, it means a lot more if I use D, but just to be consistent with your data booklet, and SB for the second segment, for part A and part B, okay? So we know that if we add these two together, we will get the total distance, okay? So let's start with SA. So I'm gonna do that over here. I'm going to be able to use the same equation, and I'm going to use the shorthand that I showed you above, the equation above, with the average speed being V and A, to label that's for part A, and this is equal to our distance traveled in that segment divided by the T time, okay, in that segment, which is 45 seconds. If we rearrange this to get SA by itself, to get the distance by itself, we get SA is equal to its speed times the time, and that is 22 meters per second times 45 seconds, which gives us 990 meters. And don't forget to save all of your digits. Okay, we can do the same thing for SB over here, and using the same equation we got for SA, the distance traveled in segment B is the velocity, or the speed we have times the time, which is 33 meters per second times 75 seconds, and taking that gives us 2475 meters as a total. So if we now have the two displacements here, we now can calculate average speed. So let's do this step by step. For SA, we have 990 plus 2475, giving us 3465. That's our total. And we have our total time, total distance. We can now calculate this. 3465 meters over 120 seconds. We get 28.875, or rounded up to two significant figures, 29. And notice that since the question is asking for speed, I don't need to write a direction here, okay? So this is how you would tackle a problem where you have to find, or if you're using some sort of average, you need to break down the two segments of motions individually and then find a way to put them back together. It's kind of like finding components, okay, or adding vector components. Break it down, put them back together, just like Lego. So example 2 is something I want you to try. And hey, the question looks very similar, but be very careful. I've added two things. I've added that the chocobo is running east in the first segment and west in the second segment. The question is now different. What is the chocobo's average velocity? So now we got to be very careful. We are including directions in this problem, and instead of the total distance for average speed, we're looking at the total displacement. What is the change in position? So we're not looking at the total distance traveled, is a change in position, okay? So I'm going to give you a chance to do the question. So pause the video right now, and I will follow this video up with solutions on fast play. Good luck. So you first start with drawing a chocobo, moving towards the east, 22 meters per second for 45 seconds, and backwards west, 33 meters per second for 75 seconds. So the average velocity here is your total displacement over your total time. To find the total time, we calculated in the last question 120 seconds, but the total displacement, now we have to be careful of directions. I'm now labeling east as positive direction, west as a negative direction. Make sure to do that for your problems, and our displacements and velocities will be different for the second part. The same first part is the same, but for second part B, notice the velocity is negative 33 meters per second going west and a negative displacement. Now if we add the two together, we're going to get a negative value because the 2475 is negative. Now, when we calculate for our average velocity with a negative displacement, we're also going to get a negative average velocity, which we put a negative sign in our answer, or we can just say the actual direction itself, west. All right, so here we go. Here are the solutions. So notice that because the chocobo run backwards, we had to use the negative value. We had to subtract the displacement going backwards, giving us a shorter displacement or shorter magnitude to work with, giving us 12 meters per second west. And you can either represent that with a negative sign, given that you've drawn your diagram of which direction is negative, or you can just say 12 meters per second west to clearly communicate the directionality there. Okay, either way works. So hopefully these examples give you an idea between instantaneous versus average velocity. We did some examples with the calculations. So hopefully this video helped you clarify a few things and will help you do some future examples. Thank you for watching. I will see you next time on Fat Mama Physics.